Okay, still on section 4.2. The last video we ended talking about some of this experimental vocabulary. We said there was quite a bit of vocabulary in this experimental design. And let's look at an example. We'll come back and look at this diagram here in just a moment. But let's go ahead and look at this growing tomatoes example and see if we can identify the experimental units and all these different elements that are taking place here. It says, does adding fertilizer affect the productivity of tomato plants? How about the amount of water given to the plants? To answer these questions, a gardener plants 24 similar tomato plants in identical pots in his greenhouse. He will add fertilizer to the soil in half of the pots. Also, he will water the plants with ½ gallon of water per day, 1 gallon of water per day, or 1½ gallons of water per day. At the end of 3 months, he will record the total weight of tomatoes produced on each plant. Problem: identify the experimental units or subjects, the explanatory variables or factors, the levels of the factors, the response variables, and the treatments. Make a design diagram, which is what we're going to do up here. So let's first identify each of these things. And again, we sort of defined what each of these things were up above here. Okay, the first thing they're asking for is the experimental units. So these are the individuals to which the treatments are being applied. Okay, so who is or what is receiving the treatment? That would be the 24 tomato plants. Okay, 24 tomato plants. Explanatory variable or factor. Okay, now remember, this is kind of like a broader category. We're not getting very, very specific here. Like in the previous example from the other video, we said music type, length of time, and we got down to the level, then we were more specific with those categories. So we want to think about this as just merely being a category. So what are we going to be doing to these tomato plants? Well, we're going to be applying, we're going to be applying fertilizer, possibly, okay? And we're going to be applying different amounts of water, okay? And we'll get specific with those amounts down in the levels, okay? So as far as the levels of fertilizer go, the options are either we're going to apply fertilizer or there will be no fertilizer applied. In terms of the amount of water, the options were either ½ gallon, 1 gallon, or 1½ gallons of water, okay? The response variable, okay? The response variable is what it is that we're actually measuring. Okay, so what are we looking to measure here? Okay, this would be right here, we're recording, it says, the total weight of the tomatoes. Okay, the total weight of the tomatoes. Okay, and then we want to say what the treatments are. So we can say how many, but then we need to list what all of those combinations are. And if you remember, we set up here that if you multiply the number in each level, that will tell you how many treatments you would expect to have, how many different combinations. Well, there are 2 to this level, there are 3 to that level. So if we take 2 times 3, we should end up with 6 treatment groups here, okay, 6 treatment groups. And so we want to identify specifically what these combinations are. Okay, it could be fertilizer with ½ gallon of water, fertilizer and 1 gallon of water, or fertilizer and 1½ gallons of water. And then the other combination is no fertilizer with each of those water amounts. Okay, and this comprises our 6 treatment groups here. Okay, our 6 treatment groups. Now, how could we describe this experiment using what is called a design diagram? Okay, and that's kind of what we have up here. This little flow chart would kind of organize how you would execute the experiment. Okay, so we're going to start with the experimental units. I'm just going to add some more details in here. That would be our 24 tomato plants. Okay, now this part here is very important if you ever are going to make an experimental design diagram, is you need to make sure that you're distinguishing that you're going to be taking these 24, they are going to randomly be assigned to one of the two groups. Okay, one of the two groups. So one group of 12 plants will receive fertilizer. That'll be the group that'll get fertilizer. And then the other group of 12 plants, they will get no fertilizer. Okay, they're going to get no fertilizer. Okay, but maybe we would flip a coin. Okay, the first plant, flip a coin. Heads, they're going to get fertilizer. Tails, they're not. And once one of the groups is full, then everyone else gets funneled into the other group. Okay, now there will be 3 treatments here. Okay, and even this part here, I probably should have designated, and I can just write here, randomly assigned. So those 12, they're going to randomly be assigned so that 4 of those 12 plants will get a half a gallon of water, 4 will get 1 gallon of water, and 4 will get 1.5 gallons of water. Okay, and you could do this a variety of ways. You could do a random number generator on your calculator and allow 1 to be a half gallon, 2 to be 1 gallon, and 3 to be 1.5 gallons. And you could just, the first plant, generate it, and whichever number, it gets put in that treatment group. Okay, but it's very, very important that you're not, the researcher is not the one who determines which treatment group it goes in. It has to be randomly assigned. Okay, and then down here we can spell out what these 3 treatment groups would look like in the no fertilizer. Okay, same thing, 4 plants, each of the 4 plants are getting a different amount of water. Okay, but these are in the no fertilizer group. Okay, and at the very, very end of your experiment, you would then compare all 6 treatment groups and see if you can draw any conclusion with whether fertilizer plays a role, with whether the amount of water plays a role in how the plants grow and what their weight would be. Okay, all right, let's go ahead and flip to the next page here. Just one more problem where we're just going to practice defining these different elements and vocabulary to an experiment. It says a cookie manufacturer is trying to determine how long cookies stay fresh on the store shelves and the extent to which the type of packaging and the store's temperature influences how long the cookies stay fresh. He designs a completely randomized experiment involving a low temperature of 64 degrees and a high temperature of 75 degrees. And 2 types of packaging, plastic and waxed cardboard. We are to list the experimental units, the factors, and the treatments. And we'll also go ahead and identify the response variable here. Okay, so experimental units, that would be the packages of cookies. Okay, this is what is having all those factors applied to it. Okay, the factors, okay, this would be remember these are broad categories. So this is the store temperature and the type of packaging. Now this problem didn't ask us for the levels, but if they did, that's when we would say the temperatures are 64 degrees and 75 degrees and the types of packaging are the plastic and the waxed. Okay, the response variable, this is what we're measuring. We're measuring the freshness of the cookies. Okay, the freshness, we want to see if they stay fresh there, of the cookies. And then the treatments. Okay, remember there were 2 temperatures, there were 2 packaging types, so that means I should have 4 treatment groups. Okay, here's my 4 treatment groups. It would be 64 degrees temperature and packaged in plastic, 64 degree temperature and packaged with waxed cardboard, and then the other combination is with the 75 degree temperature for each of those packaging types. Okay. All right. So this next box here has what are called 4 principles of experimental design. I know we've been talking about a lot of vocabulary here, but these are 4 things that if you're going to make a good experiment, you want all 4 of these components to be in your experiment. And a lot of times in stats, we try to come up with acronyms to help us remember these things. This is CCRR, okay, CCRR. Okay, the first C is comparison. Okay, and when we say comparison, what we're looking for is when you're trying to test how an explanatory variable can affect a response variable, you need to have different comparison groups, like different treatment groups. Okay, if you only have one treatment, then you have nothing to compare it to. Okay, so there doesn't have to be multiple treatments. If there's only one change that you're going to be making, like if you want to test, say, a particular diet pill to see how effective that is, then you might just have what we call a control group from which to compare your treatment group who's actually taking this diet pill. Okay, so a control group allows for just kind of a baseline, a second group where maybe they're just taking a sugar pill. They don't know that they're not taking the supplement, but you do have these 2 different groups, one that's receiving the treatment and the control group that's not receiving any treatment at all. That's what we mean by comparison. Okay, now this, I could see how the second C, which is called control, could easily be confused with thinking that's referring to a control group. But what this is talking about is it's talking about trying to control for confounding variables. Other variables that might somehow influence your response variable. Okay, so it says this is going to help you reduce the changes or the variability that you're seeing in your response variable. Okay, and it's going to allow you to better be able to draw the conclusion that it was just the explanatory variable that's causing that change or difference in your response variable. For example, if you were going to try to measure how well students were going to do on a particular test, it really would be unfair to have one treatment group take the test first thing in the morning and then another group maybe take it at the very end of the day, 9th period, because maybe the time of day, how tired you are, that could influence your performance on the test. So to try to control for the confounding variable of time of day and maybe exhaustion, you would want to make sure that all treatment groups were taking the test at the same time. Now, I don't know what the specific treatments would be. Those obviously have to be different, but you want to try to make all aspects of both or all of your treatment groups exactly the same, so that really the only difference between treatment groups is the specific treatment that they're receiving. Okay? And so I'm just going to have you make this note to yourself that you want to create similar conditions. Okay, we're talking about conditions when we're talking about control here. Similar conditions for each treatment group. Okay, the second component that should be in all experiments, and we've kind of hit on this a lot, is that we want to make sure that the treatments are being randomly assigned to the experimental unit. Okay, the purpose of doing that is it's going to create groups that are as equal as possible. Okay, we'll use people for example. You want the people in your treatment groups to be as similar as possible, meaning not one treatment group maybe is all athletes and then this other treatment group are people that are not athletic. That is creating a potential confounding variable depending on what it is that you're trying to measure. That's why if you take all the people who you've gathered for your experiment and you randomly assign them, it stands a better chance that your treatment groups are going to be nice, even mixtures of maybe some athletes, some non-athletes, so that we're kind of removing that variable from the equation. Okay, that's why random assignment is so important. Okay, and the last component is called replication. If you replicate something, it means you're repeating it over and over and over again. And so when we talk about replication, we're saying we want to make sure that you're using enough experimental units so that you feel like you can draw a decent conclusion. If you only have 3 people in each treatment group, I don't know if that's a really good indication of replication. Okay, you don't have to have extremely large treatment groups, but you want to have enough of them so that they're just not extremely small and you're drawing your conclusion from just a handful of people. Okay, so in summary here, it says, with control, randomization, and replication, we're hoping that each treatment group is nearly identical, okay? And if we can achieve that, that's when we can say at the end of our experiment that the explanatory variable in fact caused the change that we saw in the response variable, or we could say the difference in the response variable just happened to be due by random assignment of subjects to their treatment groups. So for example, if we randomly assigned people to 2 groups, and let's say some of them were athletes and some were not athletes, it's quite possible, even just through the random assignment process, that maybe 3/4 of one group is all athletes and 1/4 of the other group is athletes, okay? And that creates a little bit of an unbalance. So it's either one of these 2 things. Either your explanatory variable is actually causing the change in your response variable, or your groups were a little bit unbalanced due to just that random assignment there, okay? Okay, so we're going to wrap up on the next page here, talking about specific experimental designs. Okay, when we talk about a completely randomized design, this is when there is no sorting prior to random assignment. Okay, so you're not going to organize your subjects at all. They're just all in one big pot, and then you are going to randomly assign them to treatment groups. That's what a completely randomized design is. We talked about a control group. This is a group that undergoes no change. Oftentimes they use placebos, especially in experiments that involve like medicines and things like that. A placebo is really like essentially like a sugar pill, okay, where what you've ever heard of the term placebo effect? That's when someone ends up having a reaction to something that really wasn't there, okay? So let's say one group was given a pill for weight loss and the other group may just be given a sugar pill, but neither person in either group knows if they're actually receiving the diet pill or not. That kind of eliminates this placebo effect from happening because sometimes it changes the behavior also of the people participating in the study, and they want the results, and so maybe they're doing other things off on the side to also get those results, but then they just want to attribute it to the placebo pill, okay? All right, so we're going to just talk about a double-blind and a single-blind experiment, and we will save block design and the rest of these notes for the next video. Okay, this is really important. A double-blind experiment. This is when neither the subjects nor the experimenter know which treatment the subject is receiving. Now, it is very important that someone knows what treatment people were receiving. Otherwise, you can't properly analyze the results. So, for example, let's say that one group is given a pill to reduce cholesterol. Let's say the other group is just given a placebo pill. Both the subject and the doctor might not know which treatment was given to who, okay? And what the benefit of a double-blind experiment is it eliminates the doctor maybe from just any outside influences that would impact anything as he's analyzing the cholesterol results or anything like that. But like, there always needs to be a middleman, a researcher or someone in the middle who has a master list of who actually received which treatment. But the person who's analyzing the results maybe doesn't know who got which treatment, and obviously the person receiving the treatment doesn't know which treatment they were receiving. Double-blind experiments are a great thing. If they can ever be done, it's always a good idea to do it. Sometimes experiments, though, have to be just single-blind, and a single-blind experiment is one of two things: either when the subject doesn't know which treatment he or she is receiving, or when the experimenter doesn't know which treatment the subject received. Okay, one or the other. So it says researchers are comparing the effects of exercise versus dieting on their weight loss. Obviously, in this case, if the treatment groups were you're exercising or I'm going to have you diet, the subjects would obviously know which treatment they're undergoing. They're knowing whether they're exercising or they're dieting. But those interacting and measuring the subject's weight loss, they don't have to know which treatment was administered. Okay, again, there would be a master list, there would be a middleman somewhere in between there that would know this information, but it kind of eliminates anything happening in anyone's subconscious to somehow subconscious